Okay, so today we're going to be talking a little bit about factor score regression. Factor score regression is becoming a more and more popular alternative to structural equation modeling. This is because structural equation modeling assesses its latent variables and its causal relationships of the variables through a structural regression model simultaneously. All of that happens simultaneously, which is usually seen as a great strength of structural equation modeling, but it's actually one of its greatest weaknesses. Researchers have found because it if there's any misspecifications in the model, because everything is happening simultaneously, it's more prone to kind of proliferate throughout the entire model and can ultimately lead to unreliable estimates of parameters as well as regression coefficients. So this is really important because misinformed structural relationships are like the foundation of a lot of empirical research, or all empirical research, especially in fields like psychology, because we're looking at these latent variables and we have to trust that our observed variables, manifest variables, um, are actually measuring what they're supposed to be measuring and actually, regressing toward or not toward other variables, because all of our science is built on top of each other. And um, if we're using models that aren't accurately estimating our parameters and our relationships and these structured relationships, then it could be detrimental. So researchers have been looking for a way to estimate or to eliminate bias from their models. A lot of people have tried factor score regression. There's a few different types. But this method based off of Croon 2002 is designed to eliminate this bias. It's called the bias correcting approach. There's a bias avoiding approach, which is different, but this bias correcting approach has been found to outperform not only the bias avoiding approach, but a few other factor score regression methods, as well as SEM in some cases, which is pretty cool. It's outperformed it in some studies that have smaller sample sizes, that have misspecifications, like simulated into the data built in. It's also been shown to have like quite the comparable mean square errors, power, and type 1 error rate. It also recently has been shown to outperform SEM when in the multi-level setting, especially when the between level clusters are small. It's been shown to perform well under different types of unique factor covariances. There's only a handful of studies so far, so I'm actually just, thinking of the ones that I've read off the top of my head, which is actually probably the bulk of them, but it seems like a lot of these authors are spitting them out pretty frequently, a couple a year, over the last 10 years or so, maybe the last 5 years. So it's pretty interesting, and I think that there is some merit, some potential in the idea. So I thought it would be fun to try it out, and maybe start some kind of discussion about this new little method we've got. So bear with me, since I guess when I chose this, I didn't realize I probably should have been um, a expert in structural equation modeling first, and then this, so that I could accurately compare the two. But I'm gonna do my best and um, maybe just kind of hit the surface level, since this is new and I'm new to it and structural equation modeling. But um, yeah, we'll see how this goes. So I first libraried Levon, which is a structural equation modeling package. I libraried SEM tools, which I use for comparing the fit at the end. And I think that's all I need. Yeah, so go ahead and pop those two in. My original idea was to use some data that I've had that I was planning to use for my QRP, but I just couldn't hypothesize a structural model for it yet. I just don't know what that looks like. So I decided to generate a model based off of a model that exists by Williams and Hazer, their 1986 turnover model. It's basically a full mediation model that shows that job satisfaction and intent to leave is mediated by organizational commitment. In their model, intent to leave is also uh, regresses to turnover, but since I'm just looking at latent variables, because that's what factor score regression is used for, I'm just going to use the bulk part of that model, which is organizational commitment mediates job satisfaction, the relationship between job satisfaction and intent to leave. So generating this model was pretty interesting. Oh wait, that doesn't even work there. Okay. I set org commitment to be correlated or to be predicted by job satisfaction at a strength of about 0.8, because I want this to come out significant, obviously. And then I wanted intent to leave to be predicted by organizational commitment at negative 0.5, because that's about what it was in the model I'm basing it off of. Then I set job satisfaction with its factor loading. So basically, it's going to be made up of these 5 observed variables. Like these would each be the items that someone took on this job satisfaction survey. Same with org commitment and intent to leave. I'm calling them X1 through 5. Just for ease of application, I just made them all load onto job satisfaction at 0.8. Down here I did it with 0.7, and here I did 0.7. It's kind of arbitrary. Just wanted them to be significant, or at least just correlate highly with what they're supposed to be measuring. So these are the residual variances. It's just basically showing, like if I set it up like this, that I'm going to have a total variability of 1 in each indicator, which standardizes it. So X1 and X1 are going to be there's going to be a total variability of 1 for each indicator. So I did that for all of them, Y and Z. And so I'm going to set that as my model. or my data actually, that's generating the data. So then I'm going to set seed so it will remember that. I'm going to create my simulated data using the model above, and I want to have a sample of 200. Then I want to describe it, take a little look. So here are my observed variables. There's 15 of them because there's 5 for each of the 3 latent variables. Yeah, we can take a look at the full thing. Pretty cool, 200 for each one. Now I can set my model. So this, and I should have mentioned this before, but this is kind of the Lavon language for putting together a model. This one more specifically is going to make create the actual structural model. So org commitment is, I'm putting that it's regressed on, so job satisfaction is going to predict org commitment, and then org commitment is going to predict intent to leave. And then these are my definitions down here, just saying job satisfaction. This little equal sign and tilde basically means it's measured by these observed variables. I have it for each one. So I set my model. Then we're going to look at the descriptive statistics for my observed variables. Yeah, we've got all of these here that we created. Yeah, we looked at this earlier in the description, but I guess we can talk about it now. I basically have all 15 of these. They all have a mean, standard deviation, and maximum range of standard error. We'll just pretend for the sake of this study that the Likert scale that they were using for these surveys, for these items, was on a scale of like -2 to +2, -3 to -5 to +5, since that's kind of what the min and max seems to look like, because we're getting means like straight at 0. So yeah, that's what we are going to go with, and that's fine. That works out fine. So we can take a quick look at the factor scores. I decided to use the regression predictor for factor scores because I read an article. I read an article by Di Stefano and colleagues that said that so you can either use regression predictor or the Bartlett predictor. And like I said, I chose regression because it provides the most valid factor scores, meaning that it provides factor scores that are maximally correlated to the estimated factors. There are benefits to using the Bartlett predictor, but I figured for this being my first time, we'll just go ahead and use the regression predictor since it seems to be the best at actually choosing the best factors. So I ran a factor analysis, and here it shows me all 200 factor scores for each of my job satisfaction, organizational commitment, and intent to leave. We really don't need this. I just wanted to show how you can get your factor scores, because if you're doing this by hand, you would need to see this. So we can go ahead and start with factor score regression. This was created by Yves Rossiel. He's also one of the big researchers pushing for factor score regression with Devliger, they put out a bulk of the research on this method, kind of running with and expanding on Croon's original paper on the topic. Yeah, so Roussel, he actually created the Lavon package for structural equation modeling, and he is in the midst of creating this factor score regression method. It's actually still in like beta, and it's actually hidden too. That's why I had to use these 3 colons, because that's the only way you can get it to work. It won't just come up if you're trying to use it. But he said on Google Groups that it should work fine. It's just not public because they're still working on adding more things to it, but I think it'll be fine for what we're using it for. So I'm gonna name this, I'm gonna name this object fit Sam. It's called Sam. His first version of it was called FSR, Croon's method, but then he created a newer, supposedly more accurate version called SAM. It stands for Structural After Measurement Approach, and he says that it is identical to Croon's factor score regression if used the method local. So that's what I've got here. I've got the function. This is my model that I put up here, my data that I created, simulated data, and the method local. So we're going to run it and save it. Then we can look at the coefficients. These are basically the parameters of this model. It's way less than the structural equation model would have because it's just going ahead and creating those factor scores for the latent variable, and it's not really using all of the observed variables, so they're not being counted as parameters. I hope that makes sense, but it might if I keep going. So I can go ahead and run the summary. Like I said, I have 5 parameters. They're up here. I've only got 1 degree of freedom because I've only got these 5 parameters, because degrees of freedom in this model, I believe, is the amount of covariance minus your parameters, because I have 3 because I have 3 variables, I have 6 covariances, and then I subtract the 5 parameters and I get 1. I just couldn't have more degrees of freedom without making this model too complex, and I wanted to be able to explain it, so I think it still worked out fine this way. A lot of the models I looked at online were structured similarly. It's not like super weird or anything. This was just as big as I could make it without it being either too complex or I had it saturated at first and it wasn't giving me any fit indices. But anyways, this is what we've got. We can see that the chi-square test statistic is 19.924 and its p-value is significant, meaning that the model seems to fit, which is cool. These are my parameter estimates down here. Standard errors, basically saying 2-step was used. Like I said, there's not a whole lot of information on this exact code. So, but I'm pretty sure that the 2-step is how they estimated the standard error, and 2-step is referring to like factor score regression, like because it's stepwise. Because his version of this before was called 2-step. So I think it just uses the same type of standard error estimate. Information expected, information saturated, structured. Yeah, that's just how it's estimated. Like I said, there's not a whole lot of information on that, but here she is. So here's where it gets important. We have our regressions. These are the two that I specified in my model. I get the estimate for each regression. It's going to be the same as the standardized latent variable estimate over here. The standardized latent variable shows the results when the latent variables have a variance of 1, same as this. And then the standardized all, which is actually the coefficient, you'll see when I show the plot or the graph, that these are the coefficients, and basically this is what it's going to report, because standardized all is when not only is the latent variable standardized, but so is the observed, which is basically when they have a variance of 1. That means it's standardized. And that's kind of similar to regression, because regression is based off of, the z-score of x and y. So here we want both observed and latent to be standardized. So because, and just to go on with that, what would be a unit of organizational commitment or a unit of job satisfaction? We need them to be standardized so they're all on the same plane, I guess, plane of measurement. And then these are just the variances of each one, and they are all significant. The regressions are significant. And yeah, so I'm going to now run the this is the model. Pretty plain, pretty cute. I should have mentioned that this was standardized. That's why I'm getting these standardized estimates over here. Without it, they wouldn't have shown up. But here, I set it at standardized because I wanted it to be standardized, like I just went on that whole rant about. The style is list rule. That's just what makes it kind of cute, I guess. It makes the lines thicker the more correlated they are, and it changes the colors, and it adds the and it adds the standardized estimate for each one. So here we can see, like we saw in our regression, that this was highly predictive of job satisfaction, was highly predictive of organizational commitment at 0.71, and then org commitment was highly negatively correlated with intent to leave at negative 0.52. It's going to have the variance. This variance is set at 1 because it's standardized, as you can see here. This variance is 0.5, you can see here, and our variance here is 0.73, which matches up right here. Sorry, I'm talking so much it's making my throat hurt. So now we can look at the fit measures. We kind of, according to Rex Klein in his Guidelines of Structural Equation Modeling paper, for structural equation modeling, it's just really important that we look at the chi-square test statistic, which we already saw up here, and it was significant, so that's good. The CFI, which is a comparative fit index, and the root mean square error of approximation, which is the RMSEA, and then the standardized root mean square residual, which is SRMR. We already saw the model chi-square test was significant. Our CFI was good. A good fit of CFI is if it's greater than 0.9, and we're at 0.914, so I'd say that's pretty good. And our SRMR also met the cutoff. It's supposed to be less than 0.08, and we're at 0.076. So we're close on both of these. The RMSEA did not meet the threshold for good fit. I will say, however, that David Kinney and some other people argue that you shouldn't even compute RMSEA for low DF degrees of freedom model. My degrees of freedom is 1, so it might just not be calculating well for my model. Not to give excuses, but you know, my other 3 fits said it was pretty good, so that's that. We can also look at the correlations. You know, since this is supposed to be fully mediated, job satisfaction and intent to leave should not be highly correlated, and that's actually a pretty good correlation, but you know, it's still lower than these, so we'll pretend it's 0 for the sake of the simulated model. Yeah, so that's factor score regression, and I think it's pretty neat. I think it'll be cooler once there's maybe a little bit more to the code and just a little bit more to the entire analyses, because people are still figuring it out. But I think it's moving pretty fast, and yeah, so I think I needed to do my due diligence and check what this would have looked like in a structural equation model and see if it fit any better. In the future, maybe I'd like to run, you know, like 1,000 replications of each of these, and then I can look more at you know, bias and like proportion of successful replications. But for now, we're just gonna kind of look at those. I'm gonna run this and look at those fit indices. I wanted to do replications, but it wasn't really working. I don't know if it's because the code isn't totally done, but maybe in the future, or maybe they're hiding it for themselves, because I think they did it in their paper, but it's fine. So I'm going to call this SEM fit using my same model, same data. We're going to look at those coefficients. So like I said earlier, this one's going to have a lot more parameters because it's actually looking at the parameters with regard to each observed variable we have, these manifest variables. Let me run the summary, we can see how many there are. Yeah, so you see these are standardized because the variance at 1. We have the variances for all of these, and the estimates for the latent variables and all that. See, our number of 32 parameters and our degrees of freedom was 88. So it's kind of kicking my other one's ass. But they're technically looking at the same thing. We're just looking at the relationship between these latent constructs. So I guess however you get there is fine. My test statistic was 1059.910, and it was significant. So this model fits too. Just got to see if it fits as well as my other one did. I'm not going to go too far into all of this because this is not a video about SEM. So let's just get to the comparative fit. And honestly, a lot of this is just explained how the other summary was explained. So we can look at the SEM paths. So basically, it's showing the same fit right here. I mean, this is the point. So, we had 0.71 here, 0.7 here, and then this was 0.5, negative 0.52. Here we've got negative 0.49. So it's really close, which makes sense. It should be. It's looking, like I said, at the same thing. So let's just see how it holds up. Now, interestingly, none of these fit indexes reached the threshold of good fit. So, accordingly, the FSR analysis, considering if all of this code works correctly, it actually fit the model a little bit better. I know, I think this RMSEA is actually better than my other model, but that could be because it has a lot more degrees of freedom. Like I said, RMSEA is not good for models with low degrees of freedom. So yeah, I thought this was interesting. I mean, it does, it's in line with what a lot of these papers have been saying. So I just thought that this was pretty neat. I can go ahead and run this compare fit, which is just going to show them next to each other. It actually fits significantly better according to this. It's got all better model fit indices except for, like I said, that RMSEA, which is fine. And it just shows the differences, which I don't really need for anything because we're kind of just looking at these against each other. But yeah, pretty cool. That's all I've got for today. I hope you learned something. This was a fun class. Peace out.